Hello everyone, you are welcome to the GMAT 41's Vector Calculus class. In this class, I'll be teaching you the concept of vectors in Euclidean plane and vectors in Euclidean space. As we may have learned from our elementary calculus, a vector is a quantity that has both magnitude and direction. Of course, you have types of vectors, the zero vector, you talk about the unit vector, parallel vector, orthogonal vector, and the rest of these concepts, as we may have learned from our elementary calculus, or per se, from basic physics. And generally, vectors can exist in 3 dimensions. We could have a vector in 1 dimension, which is simply a straight line with an arrowhead. The arrowhead points to the direction of the vector, and of course the length of the line gives us the magnitude of the vector. When drawing this, the arrowhead is the terminating point. The starting point is where we started the line from, is that okay? Which you can refer to as the origin. Then again, we have vectors in 2 dimensions. This is where the concept of Euclidean plane comes into play. And we are so much used to this particular concept of vectors in 2 dimensions because, of course, we plot graphs. You can see this. This is our x and y axis shown, this graph. And you can see clearly a line drawn from the point of intersection of these 2 axes, x and y. The line is a diagonal and it represents the vector in plane. The plane there is the xy axis. Are you following right? It could also be xz axis or yz axis. The point is, in that case, we're just dealing with 2 variables. And for such vector, we can determine the position of the vector using real number ordered pairs of value, a comma b, for instance, which are real numbers, okay? If you're now dealing with a Cartesian coordinate or rectangular coordinate system, you can locate the position of that vectors using given values. Now, we also have vectors in 3 dimensions. And this is where the concept of Euclidean space comes into play. Vectors in 3 dimensions are vectors said to be in space, and they are defined by 3 variables. You can say the x, the y, and the z. You can take a look at the graph showing on the screen, and then you see clearly that there are 3 axis there. We have the z, the x, and the y axis. Alright? And of course you can see a vector drawn now. So that vector is in 3 dimensions. The position of the vector can be located using 3 other pair of values, a, b, c, to locate the position of that vector. In this class, we are going to be dealing with vectors, in component forms. We are not going to look at anything about construction, That's not the focus of this course. Not to forget also is the fact that this concept of vectors in Euclidean plane and Euclidean space is also encountered in the study of linear algebra. Okay? Alright. So, we are going to start off first by considering the concept of vectors in Euclidean plane, 2 dimensions. We're going to first treat the concept of the distance between 2 points. Just imagine you have point P and point Q with the coordinates given here, x1, y1, x2, y2 for P and Q respectively. If you've got a distance between them, how can we determine that distance? So that will now move us into the knowledge of the magnitude of a vector. Then we'll also look at the direction, that a vector in Euclidean plane can take. Now you observe that I have transferred the points P and Q into the Euclidean plane, the xy axis. And so I'm just taking here to be the initial point, of this line, which is a vector line. This is the terminating point, point Q. You can see the coordinate there, x1, y1, for point P, the starting point of the vector, and then x2, y2, point Q, the terminating point, the end point of the vector. And so what we want to do is to start from the basis of the knowledge of what we have already in basic calculus, all right, or in the study of basic physics. Now, that's under vector, of course. We want to obtain the distance between these 2 points, P, Q. And how do we obtain the distance between points P, Q? Because you can see the formula down here that the distance between these 2 points given in 2 dimensions, this R with 2 on top, stated already, it means 2 dimensions. And of course, we are going to obtain the distance between the 2 points P, Q. You see the formula very clearly written here on the board. All you just have to do to obtain the distance between these 2 points, all right, is to take x2 minus x1. That is the final value of x minus initial value of what? X. You're going to square it and then plus, do same for y. y2 minus y1, and then you square it. Take the square root of everything. Now, I'd like to say that this formula you are seeing on the board is simply Pythagoras theorem. What we've just done here is, okay, we are saying the length from here to here should be d. That's the distance, d. Now, observe something. If I decide to draw something like a slope, I'll draw the line parallel to x-axis. Let me dot it. And then this one, let me also dot it. You can see that I've gotten something like a right angle triangle, of course. That's what it is. And this length becomes what? The hypotenuse. Now, we have an angle here, theta, which we make here opposite. So this height you are seeing here is simply y2 minus y1. And then this length you're seeing here is simply x2 minus what? x1. One can play around this, just to make the point clear to you. If you dot this down, just as if you're trying to get slope. This will be the initial value, x1, of x-axis, and then this will be the final value, x2, taken from this length from here to here. And then for the y-axis, taken from this point to this point, if you dot, it will come out this way, and then this will also come out this way. Dot it, and then you get your y1 and y2. And this is simply what we're going to do now to get the hypotenuse. Simply apply Pythagoras theorem, because the hypotenuse is now the length between the 2 points we are dealing with. Which, of course, as I've explained already, that from this point to this point is simply final value of y-axis minus initial value of y-axis. And then from this point to this point is final value of x-axis minus initial value of x-axis. If you apply Pythagoras theorem, the square of this, let me indicate d here. The square of this d, hypotenuse, according to Pythagoras, is equal to the square of this opposite plus the square of what? This adjacent. And then to obtain d, you take square root of both sides. This is what it's going to give to you. So you can see how we simply obtain the distance between points P, Q. Now, just having refreshed your memory on this concept, we are now translating this into how we can obtain the magnitude of a vector, because it's exactly the same as what we've done here. Taking PQ to be a vector that moved from point P as its initial point to point Q as its terminating point. You can see the arrowhead there. We can decide to get the magnitude of this vector, and that magnitude is written as PQ. PQ. And that PQ is actually the value Q minus the value P. One can decide to take it to the origin. You now have OQ minus OP. And if you do that subtraction, it's simply x2 minus x1, and then y2 minus what? y1. So applying this to vector, saying that PQ is a vector spanning from point P to Q. The magnitude of the vector is given by this equation you have here, this formula. A magnitude sign, we simply use this slash line. Sometimes you can see the slash as a double line like this. Alright, sometimes you can see it this way, but it doesn't matter. I've used a single line, is still the same as magnitude. So what have I said so far? Exactly what we do in distance between 2 points, that is how we actually obtain the magnitude of a vector. And this is simply the concept of Pythagoras' theorem. So you don't play with this formula, okay? Memorize it, very important. Now I would like us to do something further. I would like us to do something quite interesting. Because if you look at this vector, it moved from point P to point Q. And point P here is not the origin. Now suppose I assume that I want to find a magnitude of a vector with its origin, the starting point at point 0, 0. This point, which simply means that the vector would have to move, I would kind of extend it to the origin like this, joint to this. So I'm interested in this point now, where of course, I'm going to have the value to be 0, 0, x, y value. Which means if the vector is not moving from the origin, then we are going to get x1, y1 to be equal to 0, 0. That being the case, we can come to this equation and do something. Alright, I am saying if the vector now moves from the origin. And of course, generally that is the case. We usually try to link any given vector to the origin. Even if I am to obtain PQ like this, I can write it as OQ minus OP. That O there is showing the origin. Are you following? Which by standard we take the coordinates of the origin as 0, 0 for 2 dimensions. And then for Euclidean space, 3 dimensions, 0, 0, 0. That being the case, what is going to happen here? So this is what is going to happen. The value of x1, y1 will now be equal to 0, 0. Let us come into this now and obtain the value of the magnitude. Therefore, we could say that PQ, in that case, where of course P is now serving as our origin, and that will be equal to OP. I've explained that already, because we have taken this OQ rather, OQ, because we've taken P to the origin. Are you following, right? And most cases, we simply write this as Q without bothering ourselves putting the origin there. We know that the origin is already at point 0, 0. So we could simply write this in this format. And so this is now going to give us square roots. Right. If you substitute 0 for x1, we'll be left with x2 here. And this is simply x2 squared. That x2, no need of putting the subscripts. No need for that. It's not necessary. Is that okay? And then for this, y1 is 0. We're now left with y2, which I can simply write y for it. And then I will square it. What have we learned from here? You notice that we've actually reduced this vector to what? Q. Without minding that P is the initial point. Because that point P already has been placed at what? The origin. So if I come to you and say, okay, a vector is given by the coordinates 3, 5, alright, 2 dimensions. Let's deal with that first. 3, 5. Obtain the magnitude of the vector. It's simply square root of 3 squared plus 5 squared. Is that okay? That's just what we've done here. But in the case where the vector does not move from the origin, maybe in this case, I gave you 2 points. The initial point has a value, not 0, 0. The final point has a value also, not 0, 0. Then of course, you need to apply the concept of x2 minus x1, y2 minus y1. We'll see all those when we pick question actually to deal with. Let us now conclude this part by looking at the direction, is that okay, of the vector. The direction of this vector. To obtain the direction for this 2-dimensional vector, first of all, I am going to indicate this angle, say theta. Because calculating the value of that theta would tell us the direction of the vector. And how do we obtain theta here? We all can see clearly that we can use the trig identity, tan theta. Tan theta equal to opposite over what? adjacent. Our opposite here is y. You know, this we have here, if y is equal to 0, this is also equal to y. So I can simply say that for the direction of the vector, we have that tan theta is equal to y over x. Is that okay? Y over x. And simply to obtain our theta, we have to take the tan inverse of y over x. This concept of y over x is simply telling us to do opposite over what? Adjacent. Take the tan inverse of it. And so this is what we deal with in the concept of vectors in 2 dimensions. And so we are going to move on to another concept of vector in Euclidean space, 3-dimensional vectors. Let us now look at vectors in Euclidean space, 3-dimensional vectors. On the board here, you've got the graph, showing this 3-dimensional vector. This vector PQ is in 3 dimensions. I want to say this quickly, that the concept of what we're going to learn here is actually like a more general form of the 2-dimensional vectors that we've just treated. Is that okay? Because analytically, when dealing with the arithmetics of this 3 dimensions, we can actually reduce the 3 dimensions to 2 dimensions just by eliminating one of the axes, and that's all. Anyway, back to what we have on the board. I've decided to depict, to show this vector PQ from the origin. We know already from what I discussed in 2 dimensions that P may be from another point, x1, y1, z1 in this case, which is not 0, 0, 0. But this time I just decided to draw the vector from the origin, assuming that point P is at the origin 0, 0, 0. That's the initial point. Now, one important thing about this 3-dimensional vector is that the 3 axes, z, y, and x, are held mutually perpendicular. That is, at right angles to one another. That is at 90 degrees. You want to take note of that. Alright, so what do we do here? Trying to get the distance between the 2 points PQ, and then of course it's similar to what we've treated in the 2 dimension. You've got the formula here. What we've just done here is to introduce the z-axis. Are you following, right? It's just to introduce the z-axis. So if I assume that, okay, P is not at the origin, say that P maybe is from somewhere here, alright, so you see that P will have the coordinate x1, y1, and what? z1. This is 3-dimensional technique. And so for that reason, the formula will take the form in terms of distance between the 2 points PQ, x2 minus x1 is square root, y2 minus y1 is square root, of course you're adding, then plus z2 minus z1 is square root. Take the square root of all these terms you have here. And of course this again is Pythagoras theorem extended to 3-dimensional coordinate system. With this concept above, we can actually proceed to now introduce our concept of vector, taking PQ as a vector which moves from point P to point Q. Is that okay? Then we are going to get a magnitude of vector PQ, which I told you it's simply OQ minus OP, or simply Q minus P. Don't worry, when we take questions, you would understand what I mean by this OQ minus OP, or simply Q minus P. And so the magnitude is the square root of this term, x2 minus x1 all raised to power 2 plus y2 minus y1 in bracket power 2 plus z2 minus z1 in bracket power 2. So once again, you've got to memorize this formula, very important. That's what we use in calculating the magnitude of a vector in 3 dimensions. If it's in 2 dimensions, it's simply to remove this z. Are you following, right? Or you leave the z, remove y, you'll be left with that of x and z. Or you eliminate that of x and then you'll be left with y and z. That's why I said that this is actually a more general form of 2-dimensional vectors. Now let us take our point P, the initial point to the origin now, just like we have it in this diagram, in this graph. If point P is at the origin, that tells us clearly that the coordinate of point P, x1, y1, z1 will be equal to 0, 0, 0. That's going to be the value. Is that okay? And that being the case, if we come to this formula, x10, y10, z10. The formula will reduce to this. Under this condition, we don't need to bother ourselves putting subscript 2 for x2, y2, z2. That is why here we have that x2, y2, z2 will be equal to x, y, z. These are points, they are values, they are real numbers in the Cartesian coordinate or rectangular coordinate system. And having said that, the formula will now become this: magnitude of vector PQ. Knowing that P is now at the origin, we could simply write magnitude of vector OQ. And vector OQ can simply be written as Q. I hope I'm communicating right. So we're talking about the magnitude of vector Q in 3 dimensions. And so that is going to give us this formula: square root x squared plus y squared plus z squared. So just think about a situation whereby I come to you and tell you that vector A has a coordinate 3, 1, 4. Find the magnitude of vector A. It's simply square root of the sum of the squares of the numbers that I gave to you, which is square root 3 squared plus 1 squared plus 4 squared. Simplify it and you get your answer. That's the magnitude of the given vector. Let us now move on to another concept, the concept of unit vectors. In this case of 2-dimensional vector, you notice I didn't say anything about the direction. Don't worry, we're not going to talk about that at this point. Let's move on to unit vector. We may encounter it as we move on subsequently. For now, we don't have a need for it. Now we are going to look at the unit vector. The unit vector is a type of vector that we have. And just like the name goes, unit vector. The word unit, you know, mathematically refers to 1. So a unit vector is simply a vector whose magnitude is equal to what? 1. Whose magnitude is unity. When you say unity, that means 1. Are you following, right? Good. Now you can see this graph here on the board. I've decided to use the Euclidean space graph for 3 dimensions because, like I said, 3-dimensional vector is a more general case. If you delete one of the axes, it will reduce to 2 dimensions. So I've just given it more general form. Now you notice something here that along the y-axis, I've introduced something j. Along the x-axis, you know, this line is parallel to this, so it's x-axis. I've introduced I, and then along the z-axis, I've introduced what? K. These I, J, K are specific unit vectors. Are you following, right? They are given to us as a standard. I shows us the direction in x-axis, J, direction in what? Y-axis, and then Z has K as a unit vector, which tells us the direction in the what? Z-axis. And like we stated earlier, the value, the magnitude of these unit vectors, I, J, K, is equal to 1. That is why in each of these axes, I decided to cut off a point, you can see that, and then I wrote 1 there. That is the magnitude, the value of our unit vector. How do we obtain the unit vector mathematically? Like generally, if I give you a unit vector now, and then I ask you to calculate the unit vector in the direction of that vector, all right, what would you do? The unit vector in the direction of the vector I gave to you. Please, it's important for you to know this. Unit vector is also called direction vector. You see, when I was mentioning IJK here, I told you this goes in the direction of so-so axis. So unit vector is also known as what? Direction vector. And then mathematically, it's equal to the position vector divided by the magnitude of the position vector. There's a symbol I've chosen to use for unit vector, cap U. Cap U, is that okay? Although you don't need to bother yourself pronouncing the cap. It's not necessary, it's just a symbol. Are you following, right? So the unit vector of any given vector, say I give you this position vector, find the unit vector in the direction of this vector. It is simply this position vector divided by its magnitude. And of course, from Pythagoras' theorem, I've already explained previously how you determine the magnitude of a given vector. Now, the position vector can be written to show its components. The component here are use of x, use of y, and use of z. Simply the value of the given position vector in x direction, in y direction, in z direction. This use of x, use of y, and use of z are numbers. So we refer to them as scalars. Are you following, right? Scalars. So actually this u can be written in its component form simply as u equal to use of x, use of y, use of z. And these are numbers. For example, say u is equal to, that's vector u, is equal to maybe 1, 3, 4. Is that clear? Now, if you want to combine these scalar components of this vector, you have to introduce these specific vectors ijk. So once you multiply the vector value in x direction by I, it gives you room to add it to the vector value in y direction. You multiply by j plus use of z, then times what? K. So what I'm saying in essence is that this ijk as direction vectors or unit vectors, they help us to add components of vectors. And that's what you've seen there. Just a quick example, assuming I give you that, okay, vector u, which is a position vector, is equal to 1, 3, okay, now let's say, minus 2. So what will you do if you want to add these components together? The vector u, the position vector, will now simply be equal to 1 times I, which is I, plus 3j minus 2k. Of course, that minus 2k is actually plus minus 2k. Plus times minus will give you what? Minus. Anyway, I'm just taking my time to explain the importance of these ijk unit vectors. And this form that I gave this vector is vector in 3 dimensions. It can also be reduced to 2 dimensions. If you wipe off any one of them, what is left will be vector in Euclidean plane, 2 dimensions. These ijk are actually called the basis vectors. Like I said, they are specific unit vectors. We'll call them the basis vector because they are standard. We can write them out in 3 dimensions as this. For I, I is the unit vector in x direction. So it will only have its coordinate value in x direction. You can see the magnitude 1, y and z will be 0, 0. Then j is the unit vector, the direction vector in y direction, which means that its magnitude 1 will only exist for what? Y coordinate. X and z will be 0. Similar to that of k, the unit vector in z direction, it will only have its magnitude 1 in the z coordinate. Then x and y would be zeros. In 2 dimensions, you have something similar. It's just for you to wipe off maybe the z coordinates. Alright, as you may wish. Having said this, take note of this. Magnitude of I is the same as magnitude of j. It's also equal to magnitude of k. And the value is what? 1. Remember, unit vectors, their magnitude is equal to what? Unity. That is 1. Don't worry, as we move on, we're going to verify that, okay? I'll give you a vector, we'll solve and obtain the unit vector, the direction vector in the direction of that position vector that I'm going to give, and then I'll ask us to find the magnitude of the unit vector we obtained. At the end, we'll get 1. That's okay. It is now time we're going to pick problems and solve. We've looked at the concept of how to obtain the magnitude of a vector, whether in 2 or 3 dimensions. We've considered how to obtain the direction of a vector in 2 dimensions. And then now we've also looked at how to deal with or obtain unit vectors. So we shall now proceed to solve some problems.